Morning, everyone. We are here to talk about the Scalable I virtualization. It's a next-generation framework for I virtualization for next-generation data centers.
Yeah.
My name is Utkarsh Kakaiya. I lead the Scalable I workstream in the server project. I have with me Steve Glaser.
Me or him? Okay. You're muffled. You need the mic comes down a little.
So goal of this workstream is to actually build a scalable virtualization framework. So goal of this workstream is to build a scalable virtualization framework with improved composability and scalability. Participants of the workstreams are AMD, Intel, ARM, Ampere. We also have Microsoft and Red Hat as software partners, and also Nvidia and Broadcom. We want to make sure that whatever architecture we define is supporting cross-host and also multiple device architectures. We also want to make sure that new scenarios like conversational computing are supported by this architecture as well. And we also want to make sure there's a transition path from today's architecture like SIOV to Scalable IOV. So this particular slide covers some of the design assumptions made by SRIOV when it was designed in 2007. So when SRIOV was designed, in those cases, it was more about the VF2 or VM2 host ratio was very small. It was assumed that the VF will be asymmetric, so it'll be okay to have a similar size bars across VFs. VFs will be of the same device type. MRIOV or multi-root was not into part of scope, and network virtualization also was not part of scope as part of the design. So if you look at today's world, a lot of things have changed. Let's look at I/O virtualization usages. So in terms of the compute scaling, today many of the servers have hundreds of cores, and they run hundreds of VMs. So we need more scalable device interfaces to really be able to assign each of the interfaces to each of the VMs on a cloud system. Also, many cloud service providers are moving from VM to containers. And when you move to containers, you'll be running like thousands of containers on a single host. So we need the ability to assign or scale the number of device interfaces to be assigned to each containers in a cloud environment. Also, if you look at today's world, many times we also assign the interfaces directly to the user mode application, like a DPDK or data movers. Similarly, if you look at today, many of the cloud environments, they use the multi-root systems where you assign different device interfaces to different hosts through a specialized switch. If you look at I/O management today, many of the device frameworks require a PF driver to really configure the backend resources for the device, so that way you know exactly what resources are given to which VM. And in this case, there are also scenarios we're seeing today where, imagine a scenario where you have a large VM with like hundreds of device interfaces, like work queues, and you have 20 small VMs. You want to kind of heterogeneously create different device interfaces depending upon the demand of the VM. We also see scenarios where you want to expose both NIC and storage from a same kind of a device. They also like GPUs where you have terabytes of memory, and we don't want to waste the address space by exposing same bar size across SRIOV devices. Similarly, we see like nested virtualization being more prominent in today's world, where you have a FAT-VM running with a device interface, and then you kind of subdivide that into multiple containers running in part of the VM. So in these scenarios, it's very hard for SRIOV to be applied because there's no way to subdivide a virtual function into multiple interfaces. We're also learning a lot of things about security with time, where we need to kind of intercept some of the critical registers through the hypervisor, or config space through the hypervisor as well. This is what brings us to Scalable IOV.
Yeah, one of the issues is there's a lot of stuff that's built into SRIOV that's in hardware that nobody ever uses. The software doesn't allow that hardware access, so we're actually spending a lot of cycles to build stuff that nobody's involved with. By moving a lot of the things that are in a VF into software, we're modeling what software does today and making the hardware simpler and more scalable.
So with Scalable IOV, we would like to really be able to bring better scalability compared to SRIOV, also build composability so you can compose the device interface based upon the VM's demand. So the way what we do is that we try to move the control plane to system software through virtualization software, while keeping data plane to the device to kind of keep the performance similar or same as SRIOV. And we achieved that by defining a more lighter weight composable interface called Scalable Device Interface, or SDI. So SDIs, they don't have their own configuration space on the device. So it allows us to really reduce device complexity by not requiring to build config space for each device interfaces. It also don't have its own bars as well. We reuse the PF bar where you can segment or distribute the PF bar among SDI based upon our demand. We also don't need SDI to have their own MSIX tables or MSI interrupts. They can reuse the PFMXI or some interrupt-specific storage for their interrupt assignments. And last thing, in terms of to reuse the PCI protocol and fabric, and also some of the IOMU virtualization, we felt that we could just reuse the request routing ID. So each SDI has a unique routing ID, which is used for tagging all the upstream traffic from that SDI.
Yeah, and that's a big change from SRIOV version 1, which used the pass ID more. So the goal of SIOV is to support large topologies where you can have maybe 1 million SDIs. And SDI is kind of a misnomer. It should probably be more like a scalable function, but SF is already an acronym that's used in the industry, so we didn't want to, particularly inside Linux, so we didn't want to confuse the world by reusing the same acronym. I would have preferred SFI or something, but that's done. SDI is it.
So this particular slide shows the device design example between SRIOV and the Scalable IOV. So if you look at on the left, for SRIOV, each of the VF would have its own config space, its own bars, and MSIX table. When you look at on the right side, we don't need to really have those extra logic on the device, thereby making device more scalable and reducing device complexity. Also, in terms of bars, we just reuse the PF's bar. Sometimes device also builds some kind of mapping logic which tells which of the bar gets exposed to which backend resources. By using this more composable interface for SDI, we can move all that logic into software, thereby also removing some of the mapping logic requirement for the device itself. So we move from like tens of hundreds of virtual functions to like thousands of SDI. Current spec supports up to 64,000 SDIs. We're also looking into an extension to go to up to 1 million SDIs in the future.
And SRIOV could have supported 64K VFs, but that would have required using more than one bus number, which almost no software ever supports. So SRIOV is limited to 256 unless you do more than one bus number, and nobody did that.
So this particular diagram shows the software architecture for Scalable IOV. So we try to make sure that we can leverage the current VFIO frameworks and also on Windows operating system hypervisors to actually use that knowledge and the interfaces to really get benefits from the IO virtualization. So what we do here is we create something called a virtual device, which is made up of intercept resources and direct map resources. Intercept resources is something we actually go trap it in the hypervisor and let the host emulate, thereby removing the extra logic on the device for those intercept resources. Whereas direct map resources, we directly map it to the VMs to get good performance for direct submissions and completions. So call to action mainly here is that let's work together to build this new IO virtualization framework. In terms of specification, we have two specifications. The first one is the PCI SIG ECR we have put together as an extension to PCI spec. It has been submitted to the protocol working group sometime in June. And it's currently going through the approval process. Yesterday, it was published for a member review, so we'll request PCI members here to review the ACR and provide feedback.
Yeah, the SIOV ECR is an ACR against the base 6.0 spec. It was approved yesterday, so it is now live on the PCI SIG website. Just go to the review zone and log in as a member, a PCI SIG member, go to the review zone, and you'll find it.
Thank you. The other specification we have is more of an enabling guide in the OCP, which is more of a system-level guidelines and software guidelines for the SIOV systems. We are currently working on our draft, which should be published sometime next month. We are hoping that we can gather community feedback from OCP for the enabling guide and then get to a 1.0 in sometime early next year.
Yeah, and the difference between the two is the ECN is changes to the PCI spec. So PCI specs and specs in general are this is what you must do kind of things. They don't tell you why. They just tell you what you have to do. The enabling guide is saying, yeah, this is why, and these are some other things you need to pay attention to make it all work. So anything that is not they need to be read in concert. They're not, either one is not a standalone.
So that's all we had for today. Thanks, everyone.
Hey, just a quick, Vilas Sridharan from AMD, just a question. You mentioned a lot of this is emulated by host software effectively. That's not part of the ECR, right?
No, no, but what we're basically saying is the ECR says, here's what your hardware must do.
Yep.
It doesn't say squat about what software has to do.
Okay.
PCI is pretty silent on that in general.
Okay, so the enabling guide would have essentially
Yep.
that.
And it's not what software has to do, it's here's the kind of things you ought to be doing in software. And you have this problem, please solve it.
Yeah.
Here's some hints about how you might do so.
Okay, got it, thanks.
Suresh Rajgopal, Micron. I understand the motivation to simplify the hardware aspect of it, but on the storage side, has there been any engagement with, say, NVMe on how SDIs would map to, say, queue pairs or namespaces?
We haven't had any formal stuff. Oh, okay.
Sorry, I'm Jake Oceans from Microsoft, and I have been engaging with, in the past with, SNIA, in order to talk about that. I gave a talk a year and a half ago at SNIA on how we would map an NVMe controller built with these techniques. And I've honestly just been waiting for the ink to dry on this spec before we go to the NVMe committee and define what an NVMe, a scalable NVMe controller would look like, and that's certainly something that we can discuss today. You know, if you'd like to talk afterwards, I can go into it at length.
Okay, thank you.
Thanks, Jake.
Looks like we're good. Thank you.
Thanks, everyone.
Thank you.